here, I'm going to be telling you about this, this fun little project that I've been doing with numbers. So let's play a game. I'm going to produce a set of positive whole numbers. We are going to find a way to arithmetically get it to equal the number 10. The rules are this. You must use each number, but you can't reuse numbers. And the answer must be an arithmetic expression, the four fundamental operations, but division only when it's an integer result. I'll just do this example first. I can see that 2 times 4 will give me 8. And if I just get a 2, which I can get from 7 minus 5, I can add those together. This will give me 10. So that looks like this. I'll give you this example. I'll give you a moment to think about it. So maybe you caught it. I'm not really sure, but so I see we have a 9, and we could get a 1 by taking the difference of 2 and 3, adding that to the 4. Adding those together, we get 10. There's actually also another way. It looks like this. But yeah, there can be multiple ways. This is an example with sort of like higher numbers. They don't have to be single digit. What happens when the numbers get higher, sometimes the expressions get a bit more complicated. You can see here I've had to use brackets to actually get it. It's 14 minus 4. Yeah. But now we run into this example. And this example, no matter how hard you think about it, no matter what you throw at it, you're not going to get it. This set is simply untenable. Can't believe the joke went. So we've seen that we can do this. We can get sets to equal 10. Sometimes it's a bit awkward. Sometimes it's impossible. It's also not really the most intuitive thing. Like, it's not the most obvious. So let me ask what I think is an easier question. Can we find an expression to get it equal to 0? 0 should be pretty easy. For this example, I'm picking up on like a pattern that appears a lot of places. We have all of these numbers are separated by 2. And so I can take 1 and 3, subtract, take 5 and 7, subtract. Both of those give me 2. I can subtract the 2's to give me 0. So this pattern of sort of equidistant pairs, I've noticed comes up a lot. Just thought I'd share that with you. And now, if you think about this example, yeah, I can get 10 from 2 times 5, then I can subtract the 10 away. And you might think, if I throw in another number, oh wait, I have to use all the numbers, certainly this changes everything, right? Well actually, since we can already get 0, we can just multiply the 4 away, because 0 times anything is 0. So actually, throwing in extra values doesn't really matter. This, I tried to come up with a more like sort of complicated example. It was gonna be like 28 minus 28, but the equidistant pairs pattern came up again. Genuinely, it was really hard to come up with weird examples. But there's a common pattern to all of these. I don't know if you noticed, but all we're doing here is we're taking a number and subtracting itself from it. That's really the only way we can get 0, because we can't get 0 by adding positive integers or multiplying or dividing. And then if we have any spare numbers, we multiply them away. So that is a common pattern. That's one of the reasons I think that 0 is really special for this. And here's another example. And if you try it, you can get 1, you can get 2, you can get pretty close, but you can't get 0. You can't get 0 with this example. So now, I'll just sort of set in place some terminology, and we'll formalize the problem that I'm looking at. So all of the sets that we saw before, where we were able to get 0, I will call those nullifiable, because I like fancy words. So able to get 0, nullifiable. And the weird case where we couldn't get it, innullifiable. And the innullifiable case is sort of a rarity. It's, as I said, hard to come up with. So those are what we're actually interested in today. So now let's transition a bit. Let's talk about order. We're working with sets of integers. How do you order sets of integers? How do you do that? The answer is you make a dictionary. And for this dictionary, you're going to be sorting by the highest value in a set. You're going to be sorting like this. You'll have the one set that ends in 3, then the sets that end in 4, then 5, and so on. I think you can see the pattern. If we were to actually sort by the lowest value, it would not advance. You would get 1, 2, very large number, 1, 2, another very large number, and so on. So now we have this. Let's imagine we're flipping through one of these dictionaries and we're nullifying sets as we go, finding those 0 evaluating expressions. We can do this fairly easily. We can keep doing this for a while. But where does this break? This has to break. What is the first innullifiable set in this ordering scheme? The answer is it's here. It's 1, 4, 6, 8. That is the first example of an innullifiable set that we come across. I like to call this the minimum case for n equals 4, for sets of 4 numbers. So these are sort of the big results that I have to show you today. They're the minimum cases for varying set sizes. The 3 case is pretty trivial. The 4 case I was able to work out on paper. The 5 case, I actually had to write a computer program to find this. I'll tell you more details about that later. Actually, I want to kind of illustrate, there's another way we can think about this. So if you're picking 5 numbers, 14 and less, there is necessarily some way to get 0. That's what this order means, after all, because all of the sets ending in 14 and lower have already passed. So yeah, hopefully that makes sense. And now the 6th case. And I was able to use the same computer program for this, but we're really getting into the weeds here with how many sets we're looking at. 850,000 is quite a lot. But at this stage, I started to pick up on something. What if that 15 were a 16? All of these maximum numbers would be bang on powers of 2. Is that a pattern? Is it exponential growth? Is the 7 case going to end in 64? So I checked. It does not. I was a little bit disappointed.
You were close.
It was close. Sure. Close?
Yeah.
But yeah. But importantly, this also did give me some idea that what I was looking at was original, because I typed in this sequence into OAIS. I've looked all over the place. I cannot find this. But if someone wants to point me out a 90s Russian language paper, please go ahead. And, oh dear Lord, that's a lot of sets. But yeah. 8 case, I'm still working on it, It might take a month once I set it going, but I think I should be able to get some results. So we looked at what happens before we reach the minimum case. We've looked at the minimum cases themselves. What happens if we advance beyond that? What happens beyond that? So what you're seeing here is basically a histogram. It's a log plot. So these are sets of 5. If we're looking at sets ending in 16, there are 4 examples of innullifiable sets ending in 16. Then, as we advance to 17, there's 16 of them, and so on. And it does increase, but it's not smooth, and the inconsistencies seem to have to deal with like the factorization of numbers. You see there's a big jump at 23. 23 is prime. Yeah, that's my best theory. And 25 only has 5 as a factor. So yeah, so that's quite nice. So now let's talk a bit about how I actually got these results. And let's talk about an algorithm just to verify a single set. So we're given a set as input, and let's try and test if we can for nullifiability. Now, how do we actually construct arithmetic expressions? I'm going to sort of do the intuitive method. These are all binary operations. We take 2 numbers and essentially we merge them into 1. That reduces the set down by 1 element. So now we have another integer set, and we can further test this. We can recurse, and we can systematically go through all of the different combinations of the starting numbers, all of the different operations, and if we ever get 0, that just means that we can nullify the set, but if we have exhausted everything, that means the set is innullifiable. So continuing this line of thought, we could enumerate a giant dictionary of sets to try and find these minimum cases. and we could test one by one at a time. This is essentially the brute force approach. But this approach is quite bad. The big reason is just that it does not scale well. You saw with like the 6 case, we'd have to test 846,000 sets. And those are sets of 6 numbers. Like you have to, there's hundreds of possible ways to combine just the top level 2 numbers per set. That's a bit much. There's also the fact that a computer has no foresight. A computer, you are doing the computations. Whereas we can sort of pick out on patterns. That takes a whole, a computer is a computer. That's what it means to be a computer. So let's not do that. What I propose instead is, I sort of like to think of it as the inverse approach. Instead of starting from the top and just hoping that we'll find something soon, what if we start with something that we already know is nullifiable, and work our way backwards? For example, take 156, we know that's nullifiable, and we ask, how could I have gotten here? What reduces to this? Well, I know 6 can be written as 2 times 3, right? So if I just replace 6 with 2 and 3, I know that the resulting set can reduce to 156. I know this set is also nullifiable. And I can keep doing this because there are all these things that 6 can be written as, all these pairs. And I call these mutations because it's sort of like taking one value and mutating it into multiple. We can also use the property from earlier where we can just insert extra values. Any superset is nullifiable also because you can multiply spare values away. So we can use both of these to essentially take in a single nullifiable set and knock out a bunch of larger ones. It's sort of the inverse to this merge and reduce. Okay, now let's talk about how this program actually works. I have a nice hand-drawn, which I'm just realizing fits perfectly with the color scheme. Yeah, I couldn't be bothered to make this digitally. And so what this does is I have created in memory one of these dictionaries of, say, 3 sets. And I've gone through and I have marked out in blue all of the nullifiable sets I know. So what I'll do, so I also have loaded another dictionary of 4 sets. And this is where I'm trying to find the results. What I'll do is I'll scan through that source dictionary. Whenever I reach one of these nullifiable sets, I'm going to apply this inverse reduction process. And whatever I get out the other end, I'm going to zap away in the destination. And if we keep going, if we do this all the way through with a lot of nullifiable sets, we're going to shrink our search space by so much that actually a brute force actually becomes feasible now. We have gotten rid of so much that we can just weed out all of the false positives, and it really works out nicely. So yeah, that is how I found my results. That has been my project. I don't have a slide for acknowledgements, but I'd like to acknowledge my mentor, Lei Wei, who is on sabbatical right now, and Professor Rosemary. Thank you so much. And yeah, any questions?
Is there a proof that a set is nullifiable, or is it just like brute force, nothing works?
You have to, I think what you have to do, I'm pretty sure, yeah, the proof is we checked everything, and yeah, there's no way. Yes?
What were the motivation for this project?
The motivation, I was playing this game with a friend. We were not using 10, we were using 21, and he just like beat me at it because he has 8 years of practice on me. I wanted to sort of like know why 21, and I sort of just got in. I wrote like a little program to see what is the most solvable target number, like which number has the fewest of these weird cases where you can't get it, and it turned out, oh, it's 0. Well, of course it is. Wait, what are those weird cases? Hang on. And so we just sort of like worked it out in our heads. Like, that was really cool. And then I realized, oh wait, no one's looked into this? Okay, I guess it's on me. Yeah. Yeah.
For n equals 5, and then like the leading
Mhm.
entry was like
7,
would you want
11.
the leading entry to be like, or would that leading entry ever like dip back down? Or on the next slide with the histogram,
Oh,
is there ever like does it eventually
contrast
like dip
that.
down?
So, there's this weird oddity I noticed when I was looking at sets of 7. N equals 7, the first case appears at 79. And there's actually 5 of them that end in 79. But then when you look at 80, there's none of them. And that probably has to do with the factorization of 80 compared to the factorization of 79. So yeah, that was really interesting. I'm glad you asked that. Thank you. All right.
Thank you, Jacob.
Thank you very much.